Welcome to qnawire.
So here we have two swinging objects coming towards each other. They start at rest, perfectly horizontally, swing down, hit each other, and then swing back up at an angle of 35 degrees to a maximum point. Now what we're going to do here is find the value of the ratio of mass. And to do that, we need to find their initial and final speeds, and also use the idea of conservation of energy as well as the conservation of momentum. So let's start off by finding their speeds as they attach to each other at the very bottom of their swing. To do this, we need to look at the conservation of energy. They both start off with the same potential energy because they're starting from the same height. So what we can say is that they have equal speed when they attach to each other at the bottom. And this speed is going to be equal to the following. If we know that mgh is equal to 1/2 mv squared, we start off with gravitational potential and we end up with kinetic. We can see that the speed of each is the same and it is equal to the square root of 2gh. So that's going to be our initial speed when we talk about momentum. After the collision is slightly different. Because we've raised up by a height h from our original position, let me draw it right here. This is h. What we can say is, after the collision has taken place, our final velocity, Vf, is equal to the square root of 2gh yet again, but we have to take into account the angle of theta because it's no longer going to the same height. Our height is now decreased. So it's not just h, it's h minus h cosine of theta. So now let's look at the momentum of the situation. We know this is an inelastic collision, so mv1 plus mv2 is going to equal to the masses added together multiplied by our final velocity. So we know the velocity is both initial and final, so let's put those into the equation. Mass multiplied by the square root of 2gh plus mass multiplied by square root of 2gh. Now, before I go any further, we have to recognize that one of these masses has to be moving in a negative direction. And actually, by looking at the diagram, we would say that the smaller mass, the orange ball in this case, is going to be going in the negative, and the larger mass is going in the positive. We can assume this because in our final diagram we've also got it going to the positive to the right initially after the collision has taken place. So this is equal to the two masses added together multiplied by my 2gh 1 minus cosine of theta. So from here now I can see that I have a square root of 2gh in every single situation. So I'm going to remove that and make my life a little bit easier. So I should have m, and this is going to be minus little m, plus big M is equal to m plus m multiplied by the square root of 1 minus cosine of theta. Now I want my answer in terms of small mass over large for my ratio. So let's divide everything by our large mass m. And then we can help simplify and figure out what my ratio is going to be. So I'm going to simplify that a little bit on the next slide here. I'm going to have small m over big M, negative plus 1 is equal to little m over big M plus 1 multiplied by my square root 1 minus cosine 35, because my angle was 35 degrees. And now what I can do is I can separate out the parentheses right here, the m over m plus 1, and what we will have is, so this becomes small over large M multiplied by the square root of 1 minus cosine 35 plus square root of 1 minus cosine 35. And then that gives me negative m over m plus 1. Now what you should notice is I have a small m over m on both sides of the equation. So what I'm going to do is I'm going to bring this over onto this side of the equation, and I'm going to bring my positive 1 onto this side of the equal sign. And then what I'll end up with is negative m over m minus m over m square root 1 minus cosine 35 is equal to that same square root 1 minus cosine 35 minus 1. Now I can simplify the left hand side of the equation because I have small m over large M multiplied by negative 1 minus 1 minus cosine 35, which is still equal to the square root of 1 minus cosine 35 minus 1. Now simply all I can do is take this and put it under here and calculate it. So what you should get is small m over large M is equal to negative 0.575 over negative 1.425, which of course gives us 0.403, and that's our ratio. So that's our ratio of small m over large M.